72 hours ago, the European Space Agency dropped what they're calling the closest view yet of 3I Atlas, the interstellar object that's equally captivated and terrified the world. Billions in space tech deployed. 7 Mars orbiters lined up for the shot of a lifetime. And what did we get? A fuzzy white blob, like someone sneezed right on the camera lens. Within minutes, social media blew up, not with awe, but with outrage. Amateur astronomers using just backyard telescopes were getting sharper shots of comets millions of miles farther out. Yet NASA, with its Mars Reconnaissance Orbiter, fitted with the most powerful camera ever launched to another planet, has gone totally silent. The government shutdown excuse, it's wearing thinner by the day, especially when you realize China's and the UAE's orbiters are also mysteriously quiet. By the time you finish this video, 3I Atlas will be less than a week from vanishing behind the sun, hidden from every Earth telescope during what should be its most active phase. And if Harvard physicist Avi Loeb is right, what happens next could upend everything we thought we knew about what's possible in our cosmic backyard. If you're as hooked on this mystery as I am, hit that like button and subscribe to stay updated as this story unfolds in real time. Drop a comment where you're watching from, what time it is there, and do you think we're getting the full truth about 3I Atlas? And if you want to help our community grow, share this on X, Facebook, Reddit, or your GoDaddy Messenger. Thanks for always having our backs. Chapter 1, The Photo Drop That Broke the Internet. October 7th and 8th. 2020 Gen 5 will go down in history as the moment the space community finally lost its patience. For months, we'd been building to this. 3I Atlas, only the third confirmed interstellar object ever spotted passing through our solar system, was making its closest approach to Mars. 7 spacecraft from 4 different space agencies were lined up to snap unprecedented shots. The hype was real. Scientists promised clarity answers, maybe even proof of what this thing actually is. Then the images dropped. The European Space Agency's ESA ExoMars Trace Gas Orbiter, positioned a mere 30 million km from 3I Atlas during their October 3rd closest approach, released a set of images that can only be called profoundly underwhelming. A fuzzy white dot inching across a starfield. No details, no structure. Nothing to tell us if we're staring at a natural comet or something far weirder. The backlash was immediate and brutal. Astronomy Vibes, one of X's top space commentary accounts, posted a gen-by-gen side comparison that blew up in hours. On one side, a crisp, detailed shot of Comet Lemon, taken by an amateur astrophotographer with just a basic mirrorless camera. On the other, ESA's blurry 3I Atlas image. The caption hit hard. If a basic mirrorless camera can snap Comet Lemon, why can't NASA get a clear shot of 3I Atlas passing near Mars? That post now has over 40,000 reposts and counting. But it was the followed Xanup that really struck a nerve. Billions in funding. And this is the best photo they've got. Looks more like a weather balloon in a foggy backyard. To get why people are so furious, you have to grasp the gap between what we expected and what we got. The Cassis camera on the ExoMars Trace Gas Orbiter has an angular resolution of 11.36 microradians per pixel at 30 million km. That works out to 340 km per pixel. For perspective, the estimated nucleus of 3I Atlas is only 5 to 40 Den 6 km wide. That means the entire solid core of this thing would take up, at best, a tiny fraction of 1 pixel in these shots. But here's where it gets interesting. ESA knew this going in. They knew their cameras were built to photograph Mars's bright surface from just a few hundred km away, not faint objects tens of millions of km out. Nick Thomas, the principal investigator for Cassis, admitted exactly that in the official statement. This was a really tough observation for the instrument. The comet is 10,000 to 100,000 times fainter than our usual targets. So why release images they knew would be useless? Why hype this up for months, only to hand over something that tells us nothing new? The official line. They released what they had. These are the best shots possible with the gear they've got. But the timing feels deliberate, like a pressure release valve. Almost give people something. Anything to stare at while the real data stays locked up, because let's be clear, there are better images, much better images, and they're being held back. Chapter 2, The Missing Crown Jewel. While ESA was dumping fuzzy dots, NASA's Mars Reconnaissance Orbiter, MARBRO, was capturing something entirely different. The HiRISE camera, short for High Resolution Imaging Science Experiment, is the most powerful camera ever sent to another planet. Its resolution is so sharp that from Mars orbit, it can spot objects as small as a kitchen table on the Martian surface. When 3i Atlas made its closest pass to Mars on October 3rd, HiRISE had a resolution of roughly 30 km per pixel at the object's distance. That's more than 10 times better than what ESA's cameras pulled off. If there's any structure, any weird features, anything that breaks the natural Comet story, HiRISE would have seen it. Avi Loeb, the Harvard physicist who's tracked 3i Atlas since its discovery, put it bluntly in his latest blog post: the brightest pixel in the HiRISE image will give us the best constraint yet on 3i Atlas size. We're all hoping the HiRISE team releases their images ASAP. That was October 7th. Today's October 8th, still nothing. The official excuse: the US government shutdown. Over 15,000 NASA employees, more than 80% of the agency's workforce, have been furloughed. NASA's website isn't updated. Public communications have gone dark. It's bureaucratic gridlock at the worst possible moment. But here's what doesn't add up. ESA released their images. They're a European agency, totally unaffected by US political chaos. China's Tianwen-Fuyi orbiter was also positioned to observe 3i Atlas with its moderate Zan resolution imaging camera silent. The UAE's Hope orbiter, fitted with the Emirates Exploration Imager, had a clear shot too. Nothing. Multiple space agencies. Multiple sovereign governments. Completely separate bureaucracies, completely separate priorities, and all suddenly unable or unwilling to release their best data on the most scientifically significant object to visit our solar system in years. The pattern is impossible to ignore. Social media's on fire with speculation. Some claim it's coordinated. Others say something was seen that needs careful review before going public. The more conspiracy Zan-focused, they argue the images show something so abnormal that releasing them without context would spark mass panic. That last theory sounds crazy until you remember what's been happening with amateur observations over the past week. Because while the pro-space agencies have clamped up on data, backyard astronomers have been capturing images that raise more questions than they answer. Chapter 3. When amateurs see what professionals won't show. On October 3rd, the exact day 3, Atlas made its closest pass to Mars. A Portuguese amateur astronomer, known online as Dobsonian Power, uploaded an image that blew up overnight. Using nothing but a backyard solar telescope and some heavy digital enhancement, he captured what looks like an angular structure inside 3i Atlas dark geometric shapes, protrusions that don't match the soft fuzzy glow of a comet's coma. His caption was simple, but loaded with unspoken questions. What on earth is this? In 6 hours, the image spread across every major astronomy forum, subreddit, and social platform. The reaction split the community cleanly into two camps. One side saw clear proof of artificial structures, evidence 3i Atlas isn't what mainstream science claims it is. The other wrote it off as classic pareidolia. The human brain's trick of seeing patterns where there's nothing but random noise amplified by glitches from using the wrong gear. The debunkers had solid technical ground. Solar telescopes use specialized filters for the sun's blistering brightness, not faint, interstellar objects zipping through space. The equipment was never built for this. Add aggressive digital tweaks to fix the bad setup, and you're basically asking an algorithm to invent details that aren't real. It's like enhancing a blurry photo until you start seeing faces in TV static, just for astronomy. But here's where the story gets messy. Dobsonian Power isn't some random conspiracy theorist with a cheap telescope and a click-Jan-hungry agenda. He's a respected amateur who's shared legitimate astrophotography for over a decade. His YouTube channel is full of detailed breakdowns of his gear, his methods, his image gen processing steps. This isn't someone faking evidence for views, and when pressed about the weird structures in his 3i Atlas shot, he didn't double down on wild claims. Instead, he leaned into uncertainty. He vowed to try again in early November, once the object is visible from Earth again, after passing behind the Sun. His response was measured, scientific, appropriately cautious, which makes the pushback against his image even more telling. Within 24 hours, multiple websites ran articles specifically debunking his capture. Amateur telescope snaps, strange 3i Atlas image. Here's why it's a trick of the eye. The timing felt coordinated. Almost rushed, the tone read defensive, like someone needed to shut down the weird structure talk fast before the image gained too much momentum. Then the enhancement wars kicked off. Users on Reddit, X, and conspiracy forums started grabbing the original ESA images and running them through their own tools. Some used standard astronomical image Jansz stacking techniques, the legit way to sharpen faint shots. Others tried AI upscaling tools designed for boosting low Jan res photos. A few went all Jan in with machine learning models, trained to fill in fine details from sparse data. The results were all over the map. Some just showed slightly sharper versions of the same fuzzy dot. Others revealed what looked like distinct geometric patterns edges, shapes too regular to be natural ice and rock. The problem? Once you start aggressively processing an image, especially with AI, you're not looking at what's actually there. You're looking at what the algorithm thinks should be there, based on its training data. If you train an AI on thousands of spacecraft photos, then ask it to enhance a blurry dot, it might invent spacecraft Jan-like details, just because that's what it's learned to recognize. It's a scientific dead end, wrapped in the illusion of clarity. But these enhanced images had an unintended effect. They muddied the water so badly that telling legitimate amateur observations from outright fakes became nearly impossible. Within 40 Gen 8 hours of ESA's photo drop, dozens of enhanced versions were circulating online. Some showed metallic surfaces, others depicted what looked like solar panels or antenna arrays. A few even added running lights and visible thrusters, obviously fake digital art made by people with too much Photoshop skill and too much time. But mixed in with the noise were a handful that felt different, subtler, less sensational images that showed just enough unusual regularity to make you pause, to wonder if something real was being buried under the flood of obvious hoaxes. Chapter 4. The Sea-Chan leak that won't disappear. On October 4th, an anonymous user on Suchan's paranormal board dropped what they claimed was insider info on 3i Atlas. The post was titled Plain and Simple, ESA Data Leak. It opened with a credential claim specific enough to sound real, but vague enough to stay anonymous. I'm a doctoral researcher working with the European Space Agency, with ongoing access to the combined observational data on 3i Atlas. Internet leaks are a dime a dozen. Most get written off as creative fan fiction or outright trolling. But this one was different. The level of technical detail was unsettling. The poster didn't rant about alien invasions or secret military ops. Instead, they laid out 3 specific observational anomalies that, if true, would completely upend what we think we know about 3i Atlas. Anomaly 1. The chemical impossibility per the post. Spectroscopic analysis shows 3i Atlas is spewing roughly 100 kg of nickel gas every second but almost no iron. In normal stellar and planetary chemistry, nickel and iron are inseparable twins. They form together in supernova explosions. They travel together through interstellar space. They show up together in comets and asteroids. Finding nickel in abundance with basically zero iron is like finding smoke without fire. It breaks the basic rules of how matter behaves in natural cosmic environments. Anomaly 2, the thermal contradiction, the object spewing huge clouds of gas and dust classic for an active comet. Heated up by the sun, but infrared observations, they show it's cold. Way colder than it should be, given how much gas it's letting off and how close it is to solar radiation. The poster put it bluntly. It's like watching someone sweat profusely in a freezer. The physics don't match what we're seeing. The precision trajectory the post nodded to what Avi Loeb has been saying publicly. 3i Atlas arrived with an orbital inclination of just 4.89 degrees relative to Earth's ecliptic plane. But the Suchan poster added a detail Loeb didn't highlight. The trajectory isn't just unusual, it's a perfect straight shot from the direction of the galactic core. No wobble, no deviation, no signs of gravitational tugs from nearby stars during its millions or billions of years traveling through interstellar space. As if it was aimed. Then came the part that turned this from interesting speculation into something darker. The poster claimed 3i Atlas fits the profile of what they called a post-Jan biological entity. Not a natural comet, not a regular spacecraft, but something in between. They described it as having a 3-Jan phase particle engine with an estimated 70 Jan 5 Jan megawatt output, continuously transmitting an active signal and, in their words, probing our solar system. The post ended with a wild theoretical framework. 3i Atlas might be a macroscopic quantum object, specifically a Q-Jan ball. It's an exotic idea from particle physics, a type of non-Jan topological soliton that could theoretically exist at scales way bigger than subatomic particles. If stable, a Q-Jan ball could have properties that seem impossible under normal physics. It could be insanely dense while looking diffuse. It could absorb and redistribute energy instantly across its entire structure, explaining that thermal contradiction. It might even solve the nickel without iron problem. If the QZambul's internal quantum state favors certain isotopes. Within 18 hours, the post was screenshotted and shared across Reddit, X formerly Twitter, and dedicated UFO research forums. A thread about it on Conspiracy racked up over 2,000 comments before moderators locked it for unverified claims. But locking the thread didn't kill the conversation, it just pushed it to other platforms, splitting into dozens of parallel discussions, each twisting the original post in new directions. Some fixated on the chemical anomalies, others dived deep into the QZambul hypothesis. A few even started linking it to old claims that 3I Atlas might be the source of the 1970 Gen 7 WOW signal. Chapter 5, the 50 Gen 1000 km question. On October 4th, NASA's Perseverance rover, parked in Mars' Jezero crater, snapped something unusual in the Martian night sky. The image from its right navigation camera showed an elongated streak of light, roughly 4 times longer than it was wide. At first glance, it looked like a textbook long-down exposure shot of a moving object. Comets and asteroids often blur like this when cameras track stars instead of the object itself. Standard stuff, except the math didn't add up. When amateur analysts crunched the numbers using Perseverance's known camera specs and 3I Atlas's distance at the time, they landed on a disturbing figure, 50,000 km long. That's not a comet nucleus. That's not even a comet with a tail. That's something else entirely. For context, Earth's diameter is less than 13,000 km. If this streak represented 3I Atlas's actual size, we were staring at an object nearly 4 times wider than our entire planet. Social media erupted. Was 3I Atlas a massive cylindrical craft? Had it hidden its true size and shape behind a fuzzy cloud of gas and dust this whole time? The timing felt intentional. This image surfaced just one day after the Mars flyby right, when every professional space agency went mysteriously quiet. To some, it was proof. Something deeply abnormal had been photographed and it couldn't be brushed off easily. The speculation got so loud that Representative Anna Paulina Luna, a US Congress member, known for her focus on unexplained aerial phenomena, reached out directly to Avi Loeb for his take. Let that sink in. A sitting member of the House of Representatives felt the need to contact a Harvard physicist about a Mars rover photo. That's not standard protocol. It suggests someone in official circles was worried enough to bypass NASA's usual communication pipeline for an independent expert's opinion. Loeb's response was thorough, and on the surface, reassuring. He calculated that Perseverance's navcam has an angular resolution of 0.33 milliradians per pixel. At 3I Atlas's distance that day, about 30 Gen 8 million km, that translates to approximately 12,500 km per pixel. The streak spans roughly 4 pixels, which gives you that 50,000 km length. But Loeb argued this was a composite imaging artifact. The streak wasn't the object's size. It was the path 3I Atlas traced across the Martian sky during a long stack of exposures, likely around 10 minutes. His logic was airtight. Mars orbits the Sun at 20 Gen 4 km. 3I Atlas was moving at 60 Gen 7 km relative to the Sun, in the opposite direction. That gives a relative speed of over 90 km compared to Mars, over 10 minutes. That's exactly 50 Gen 4000 km of travel, perfectly matching the streak's length. The shape wasn't the object itself, it was the object's motion, smeared across time. Case closed. Right, the cylindrical craft theory debunked by basic physics and careful math. But then Loeb added one sentence, a qualifier, that conspiracy theorists grabbed like a lifeline. If the navcam images represent single snapshots with an exposure time below 3.28 seconds, then the brightness and angular length of the observed source imply that it is not 3I Atlas. In that case, the source might be much closer to the camera, capable of being smeared into an elongated image with a smaller spatial size and a smaller speed. Wait, if these are single Zen frame captures, then what Perseverance photographed wasn't 3I Atlas at all. It was something else, something closer to Mars. That line opened a door no amount of later clarification could fully shut. Because NASA hasn't confirmed if the image is a composite or a single frame. They haven't released the metadata. No exposure time. No number of stacked images, nothing. The government shutdown excuse applies here too. No staff to process requests, no one available to confirm even basic technical details about how the photo was taken. Chapter 6, 8 Years of Silence. August 15th, 1970. Ohio State University's Big Ear radio telescope picked up a 70 second burst of radio energy. So unusual, so perfectly structured, that astronomer Jerry Amon circled the printout and scrawled one word in red pen: "Wow," for nearly 5 decades. That signal has stayed one of the biggest mysteries in the search for extraterrestrial intelligence, CT. It came from the direction of Sagittarius, near the constellation's densest starfields. It was narrowband, focused on a single frequency, and it never repeated. Hundreds of follow-up observations, thousands of hours of listening to that same patch of sky. Nothing. Just that one blip 8 years ago. Then total silence, until A.V. Loeb ran the numbers on 3i Atlas. Loeb calculated where 3i Atlas was on August 12, 1970, 3 days before the WOW signal was detected. The answer: roughly 600 astronomical units, or from Earth, 600 times the distance between our planet and the Sun. But more crucially, he mapped the direction 3i Atlas was coming from back then. Right ascension 19 hours 40 minutes, declination 19 degrees. The WOW signal. It originated from right ascension 19 hours 20 minutes. Declination -20 7 degrees. The two directions are just 9 degrees apart. In the vastness of space, where objects could come from any direction, the probability of that alignment is about 0.6%. Not impossible, but deeply suspicious. Loeb didn't stop there. He asked the obvious next question. If 3i Atlas sent the WOW signal from 600 RU away, how powerful would its transmitter need to be? The math is straightforward. The detected signal intensity was 50 to 212 Janskis across a 10-cast bandwidth. At 600 RU, that translates to a transmitter output of 0.5 to 2 gigawatts GBO. For context, a typical nuclear reactor on Earth generates about 1 GW. We're talking nuclear XAN-powered XAN plant levels of energy focused into a narrow radio beam. Not impossible for an advanced civilization. In fact, it's pretty logical if you want to send a detectable signal across interstellar space without wasting energy on omnidirectional broadcasting. There's another detail that makes this connection harder to brush off. The WOW signal was observed at E10C by Arshadant Suwu, Liu MHD. Blue gen shifted by roughly 10 km toward Earth, relative to the hydrogen line, a frequency naturally emitted by hydrogen gas. That blue shift means the source was moving toward us. Today, 3i Atlas is approaching the Sun at approximately 60 km. Loeb suggests a plausible scenario. If this object has maneuvering capability, it could have been moving slower in 1970 Gen 7, then accelerated after detecting habitable Gen zone planets in our solar system. A reconnaissance pulse, a radar scan, checking for signs of technological civilization before committing to a closer approach. Here's what makes this whole link so frustrating. Verifying it would be trivial. Point a radio telescope at 3i Atlas. Listen at the hydrogen line frequency. If it's transmitting, we'd know within hours. If it's silent, the WOW signal connection is probably a coincidence. Simple test, definitive answer. And yet, as Loeb noted in his latest blog post, not a single radio telescope has reported data on 3i Atlas. The very large array, VAHA, hasn't looked. The Arecibo telescope, once a cornerstone of radio astronomy, is destroyed. The Green Bank telescope hasn't published any observations. Even SETI, the organization literally dedicated to finding extraterrestrial signals, hasn't publicly announced any monitoring efforts. The silence from the radio astronomy community is deafening. Chapter 7, The Path That Shouldn't Exist. Imagine throwing a dart at a globe from across a football field while blindfolded. Now imagine that dart not only hits the globe, but lands within a few degrees of Earth's equator. That's the level of statistical improbability we're staring at with how 3i Atlas entered our solar system. Interstellar objects can come from any direction in the sky. They should be scattered randomly across the celestial sphere, arriving at every possible angle. And yet 3i Atlas showed up with an orbital inclination of just 4.89 degrees relative to Earth's ecliptic plane. Less than 5 degrees. That puts it in less than 1% of all possible arrival angles. Avi Loeb has hammered this point in every interview, every blog post, every public statement since July. This trajectory isn't just unusual, it's statistically bizarre for a random interstellar object. To get why, you need to think about how things move through the galaxy. Stars in the Milky Way's disk orbit the galactic center at a steady average speed, but they also have random wobbles up and down, side to side like bees swarming a hive. That randomness means objects ejected from other star systems should hit our solar system from all directions with roughly equal chance. There's no cosmic highway funneling visitors into our ecliptic plane. And before you wonder if objects from the Milky Way disk naturally arrive at shallow angles, Loeb already addressed that. The galactic disk itself is tilted about 60 degrees relative to our solar system's ecliptic plane. That's over 12 times steeper than 3I Atlas's angle. If this object came from a typical star system in the disk and was ejected randomly, we'd expect a steep approach, not a gentle one. The alignment is backwards from what galactic geometry predicts. Compare 3I Atlas to the only other interstellar objects we've ever detected. Oumuamua, 2017, orbital inclination of 120-3 degrees wildly tilted, coming in from above the solar system plane. R. Borisov, 2019, inclination of 40-4 degrees, still steep, still exactly what you'd expect from a random interstellar comet. Both behaved like natural visitors. 3I Atlas is the outlier, the anomaly, the one that breaks the pattern. Loeb calculated the probability of this alignment, less than 1%. Some colleagues pushed back, saying his stats were too strict. Maybe the true probability is 5% or 10%. Once you account for observational biases, fine, even at 10%, that's a 1 Zen in Zen 10 shot. And we've only found 3 interstellar objects ever, the odds of the third being the rare exception instead of the rule. Not in favor of coincidence. Now stack this on top of everything else. The wow, signal alignment, also less than 1% probability. The chemical oddity nickel without iron, a thermal contradiction, cold, but spewing gas like a heated comet. The missing high-res images from NASA, China, the UAE all silent. The US government shutdown hitting exactly when we need NASA most. Any single one of these could be explained away. Coincidence, measurement, error, bureaucratic mess. But when you start piling anomalies on top of each other, when you multiply those small probabilities together, the just a coincidence argument gets harder to swallow. There's a statistical principle called the prosecutor's fallacy, mistaking unrelated low-jan probability events for a pattern, like getting 10 heads in a row and assuming the coin is rigged instead of just flipping it enough times. Skeptics will say that's what's happening here, a natural comet that just so happens to check a few unlikely boxes. Unlikely, sure, but not impossible. But the counter-argument is just as strong. If something walks like a duck, quacks like a duck, swims like a duck, and has duck DNA, at some point you have to consider it's a duck. Or in this case, if an object arrives on a statistically impossible trajectory, has chemical signatures no natural process can explain, lines up with a 40-8-year-old unexplained radio signal, and makes multiple governments hide their best data maybe, it's worth asking if we're not looking at a random chunk of ice and rock from another star system. Chapter 8. When questions become dangerous. Something strange began unfolding around October 5th. Users across platforms started reporting their posts about 3I Atlas were disappearing. Not flagged as misinformation, not hidden behind a warning, just gone. A Reddit user documented posting a deep dive thread analyzing the chemical anomalies from the alleged ESA leak. The thread took off. Hundreds of upvotes, dozens of comments within 2 hours, then it vanished. No moderator note, no explanation. When they tried to repost, the submission wouldn't go live. They'd been shadow banned. No notice, no reason given. On X, formerly Twitter, the pattern was similar. Astronomy Vibes, the account that went viral slamming ESA's blurry photos, reported a massive drop in engagement after October 7th. Posts that usually hit tens of thousands of people were suddenly stuck at a few hundred views. No official restrictions, no warnings, just algorithmic suppression. Quiet enough to deny, but aggressive enough to work. Other space-side astronomy creators noticed it too. Videos about 3 Atlas that should have performed well got a fraction of their usual reach. YouTube had its own tactic. Creators who posted analysis videos speculating about 3 Atlas started getting demonetization hits. The excuses varied. Some were flagged for discussing sensitive topics without proper context. Others got labeled potentially misleading content about scientific matters. A few got hit with the vague, ominous tag, content that may not be suitable for all advertisers. The rule was clear. You could make a video saying 3i Atlas is just a comet, mainstream science has it right, and it stayed monetized, even promoted. But suggest there might be anomalies worth digging into. Suddenly your video was advertiser-Xian unfriendly. Facebook's approach was the most brazen. Its fact-Xian checking system, run by third-Xian party groups, started aggressively tagging 3i Atlas content. Posts sharing the Suchan leak got missing context warnings. Claims about trajectory anomalies were marked partly false, even when the post was just quoting A.V. Loeb's published calculations word for word. The fact-Xian check articles all hit the same note. Space agencies confirm no threat from interstellar comet. Experts say unusual features likely natural. The subtext was louder. Don't worry. Don't ask questions, trust the authorities, move on. The timing felt coordinated. All of this ramped up within 48 hours of ESA's photo release, right when public frustration over the lack of good images was peaking. This is the kind of pattern that makes conspiracy theorists feel vindicated and makes skeptics roll their eyes at overreach paranoia. Because here's the thing, social media suppresses content all the time. Algorithms change. Engagement dips, fact-gen checkers flag bad info. These are normal platform moves. Unless there's a pattern, unless it's all happening at once, targeting one topic. At the moment, public interest is highest and official answers are thinnest. Some creators started using coded language to dodge suppression. Instead of 3i Atlas, they said the visitor or the object. Instead of alien or extraterrestrial, they used non-Xian terrestrial or anomalous. It was like watching people invent a secret vocabulary to talk about something platforms didn't want discussed openly. The Streisand effect in real time. The more content got suppressed, the more people assumed there was something to hide. The more aggressively fact-Xian checkers pushed back, the less people trusted the official story. Every attempt to control the conversation only fueled the suspicion that the conversation needed controlling. Chapter 9. The Moment We Can't Watch. October 20, Gen 9th, 30th. Mark these dates. In less than 72 hours from now, 3i Atlas will reach perihelion, its closest pass to the Sun. It'll swing by at roughly 202 million km, just inside Mars orbit. For a natural comet, this is make Xian or Xian break. The moment of truth, the intense solar radiation at that distance, should trigger dramatic outgassing, maybe even fragmentation. We've seen it before. Comets get too close to the Sun. The heat overwhelms them, and they shatter into pieces. Spectacular when it happens. And if 3i Atlas is just a random chunk of ice and rock from another star system, that's exactly what should go down. But here's the kicker. We won't be able to watch it. 3i Atlas will be on the opposite side of the Sun from Earth during its perihelion pass. Every ground-Xian-based telescope on our planet will be useless. The object will vanish in the solar glare, completely hidden during what should be its most active, most revealing moment. Some call it unfortunate timing. Others see it as suspiciously convenient. If you wanted to do something without being watched, you couldn't pick a better window. A.V. Loeb has been explicit about what comes next. In his October 3rd blog post, published the same day as the Mars flyby, he laid out two scenarios. If 3i Atlas is natural, it may erupt in a flare of outgassing or break apart into icy fragments soon. The Sun will dump gigawatts of power onto its surface, he wrote. That energy has to go somewhere, and for ice and rock that means vaporization, sublimation, maybe even structural failure. If it's technological, it may maneuver to use the Sun's gravity as a slingshot, or release probes that could intercept Earth or other planets, thanks to its retrograde orbit, moving opposite to how planets circle the Sun. Read that again, release probes that could intercept Earth. He's not talking about passive observation anymore. This is active deployment. The retrograde orbit is key. 3i Atlas is moving against the planetary flow, so any probe it drops doesn't have to fight that motion to reach us. It can just slip into an intercept trajectory and let orbital mechanics do the work. From behind the Sun, hidden from our view. Launching something toward Earth would be trivial. We wouldn't detect it until it was already close. Loeb went further. No metaphor, no hyperbole. When you look at the Sun in the coming weeks, Remember, 3i Atlas is passing behind it. If it maneuvers toward Earth when it re-emerges on the other side, financial markets may crash. He's not guessing. Stock markets panic at uncertainty, and the uncertainty of a potentially non-ZANT natural interstellar object actively changing course toward Earth. That's existential, ZAN-level chaos. The timing of everything only cranks up the tension. The U.S. government shutdown has NASA offline during this critical observation window. The best Mars flyby images are still locked away. Amateur astronomers can't track 3i Atlas for the next month. It's too close to the Sun. Radio telescopes haven't checked for transmissions. We're flying blind into the most important moment of this entire encounter. Whether by bungling or design, we've ended up with a situation where we won't know what 3i Atlas did at perihelion. Until it's already done, there is one group watching, the Galileo project led by Loeb himself. It runs 3 observatories, one in Massachusetts, one in Pennsylvania, one in Nevada, equipped with high-gen resolution cameras, infrared sensors, and radio receivers built specifically to spot anomalous aerial phenomena, or APs. From late October to early November, all 3 sites will be at maximum operational capacity, scanning the skies for anything unusual. If 3i Atlas releases probes, if UAP activity spikes during its perihelion pass, the Galileo instruments might catch it. Might is the operative word here. 3 observatories cover a tiny fraction of Earth's sky. If whatever comes, if anything comes avoids those specific patches, we'll miss it completely. Chapter 10. What comes after? Early November. That's when 3i Atlas will finally peek out from behind the Sun. Visible again from Earth. Ground-based telescopes will lock onto it once more. We'll learn 2 critical things. Did it survive perihelion intact, or shatter under the Sun's heat? And did its trajectory shift, even a little, from the path it entered with? After 4 months of speculation, conspiracy theories, and unanswered questions, we'll finally know if this was all just collective hysteria, or if we're staring at something far stranger than a natural comet. The 2 possible truths: if 3i Atlas emerges on the same trajectory it had before, if it's fragmented or spewing more gas in a way that lines up with solar heating, if it acts exactly like Ari Borisov did when it swung by the Sun in 2019, then the mystery closes. It's a natural comet. Unusual chemistry. Sure, a statistically wonky trajectory. Granted, but ultimately just an icy leftover from another star system passing through ours. A wow. Signal link becomes a coincidence. The Suchan leak becomes creative fiction. The missing NASA images become red tape from a government shutdown. Everything slides back into the comfortable box. Interstellar objects are interesting, but not alarming. But if it doesn't behave that way, if 3i Atlas comes out with a changed course, subtle enough that outgassing can't explain it, if radio telescopes finally point at it and pick up structured signals, if NASA's images ever surface and show geometric shapes that don't belong on a chunk of ice and rock, then we're in uncharted territory. Not just scientifically, socially, politically, economically. Every assumption about our place in the cosmos gets torn up. Every government's plan for extraterrestrial contact gets tested in real time. The Loeb scale where we stand now, Avi Loeb created something he calls the Loeb scale, a ranking system for how likely an object is to be artificial and how threatening it might be. Rank 1, almost certainly natural, with explainable quirks. Rank 10, definitely artificial, with proven hostile intent and the ability to reach Earth. Loeb has said publicly he won't rank 3 Atlas lower than a rank 2. Even in the best case, the anomalies are too persistent, too many, too linked. A rank 2 means probably natural, but with enough unexplained features to demand serious investigation. It means we can't rule out artificial origin, not yet. That's where we are right now, suspended between random space rock and possible technological artifact, waiting for November, waiting for high-gen-res images that might never come, waiting for radio observations that haven't happened, waiting to see if 3i Atlas either fades away on its hyperbolic path out of the solar system, or does something that forces us to admit we are not alone, and we are not ready. The JUICE mission. 7 more months of waiting. The SA has announced its Jupiter Icy Moons Explorer. JUICE spacecraft will observe 3i Atlas between November 2nd and 20 Gen 5th, right after perihelion when the object should be at its most active. But here's the catch. The data won't be available until February 2020 Gen 6. 7 months. 7 months to wait for images captured in November. 7 months of wondering if the activity juice sees is just normal comet outgassing, or something else. 7 months of asking, was that fuzzy dot the SA showed us in October really the best they had? Or are they carefully managing a revelation they don't know how to deliver? What this says about us, whatever 3i Atlas is, whatever it does in the coming weeks, it's already revealed something vital about our civilization. We don't trust our institutions to tell us the truth about something this big. We don't buy the official reassurances. We see patterns in shutdowns and data delays, real or not, because we've learned sometimes conspiracy isn't a theory. Sometimes it's just early reporting on what later becomes confirmed fact. The mystery of 3i Atlas isn't just about a space object. It's about us, how we handle uncertainty, how we question power, and how we prepare for a future where we might not be the only intelligent thing in the cosmic neighborhood. Chapter 1. The Invisible Visitor. On October 1st, 2020 Gen 5, a rock roughly the size of a giraffe slipped between Earth and our orbiting satellites. It came closer to our planet than the International Space Station itself. We had no clue it was coming. By the time astronomers finally spotted it, Asteroid TF was already gone, slipping back into the black of space like a shadow that never bothered to knock. Let that sink in. We live in an age where we can photograph distant galaxies forming billions of years ago, yet a rock close enough to practically graze our atmosphere went completely unnoticed until it was already in our rearview mirror. If that hits you as unsettling and fascinating as it did me, hit that like button and subscribe to stay updated on these cosmic close calls and the wild mysteries unfolding above us. Drop a comment, where are you watching from? What time is it there? And do you think we should be more worried or more amazed by how much we still miss in the night sky? If you want to help our community grow, share this on X, Facebook, Reddit, or your GoJan to Messenger. Thanks for always having our backs. This asteroid was between 1 and 3 meters wide, small enough that if it had plowed into our atmosphere, it would have burned up as a blazing fireball. Nothing that could threaten cities or civilizations. But here's the question that's keeping astronomers up at night. If we can't reliably spot something this close, something moving so fast it could cross from New York to Los Angeles in under a minute, what else might we be missing? ESA and NASA track thousands of near-Earth Earth objects, NEOs, carefully cataloguing which ones pose the biggest collision risk to count as potentially hazardous. An asteroid needs to be at least 140 meters wide and follow an orbit that brings it within 7.5 million km of Earth, roughly 20 times the distance between us and the Moon. Asteroid TF is way below that size cutoff, which partly explains why it evaded detection. Our telescopes and survey systems prioritize the big ones, the civilizations and enders, the rocks that could trigger another extinction event if they hit at the wrong angle. But this tiny visitor is a reminder: space isn't empty, it's swarming with debris, ancient chunks left over from when our solar system formed. Pieces of shattered worlds that never quite became planets, remains of collisions that happened back when Earth was still young. Most of this stuff stays far out, locked in stable orbits in the asteroid belt between Mars and Jupiter, or drifting in the distant Kuiper belt beyond Neptune. But gravitational tugs, subtle pulls from Jupiter's massive gravity, or a gentle nudge from a passing comet, can yank those orbits off course, sending rocks on new paths that sometimes cross ours. What makes TF really stand out isn't just how close it got. It's that it showed up during a month when the sky's been unusually busy with cosmic visitors. Chapter 2. The Brightening Wanderer. While one cosmic traveler slipped past us unannounced, another is making a much more theatrical entrance. Comet CT Lemon, named after the Mount Lemon observatory that discovered it, is brightening in our October skies. Astrophotographers around the world have captured stunning images of this ancient icy visitor as it hurtles toward a close approach with Earth. Unlike the stealth asteroid TF, Lemon has been tracked meticulously since its discovery, and right now it teeters on the edge of naked eye visibility. Under dark, clear skies, you might soon spot it as a faint smudge with a ghostly tail stretching away from the sun. Comets versus a cosmic dichotomy. Comets like Lemon are fundamentally different from asteroids. While asteroids are rocky or metallic relics of the inner solar system, comets are icy bodies born in the cold, distant reaches of the Kuiper belt or Oort cloud, often called dirty snowballs. Their nuclei contain frozen water, carbon dioxide, methane, ammonia, and organic compounds, the building blocks of life, As a comet approaches the Sun, solar radiation heats its surface, causing ice to sublimate, turning directly from solid to gas. This creates a glowing coma, a temporary atmosphere, and two tails, a dust tail pushed by sunlight and an ion tail blown by the solar wind, both always pointing away from the Sun. Lemon, a green comet in the spotlight. Lemon's journey has been nothing short of spectacular. Initially predicted to be a faint comet, it defied expectations by brightening rapidly from magnitude +16 in July to +6 by October 2020 Gen 5, placing it at the threshold of human vision. Optimistic forecasts suggest it could reach magnitude +2.5 by late October, making it visible even from cities with minimal light pollution. Its striking green coma is caused by the fluorescence of cyanogen, CN, and diatomic carbon, CaD, molecules under ultraviolet sunlight, a phenomenon unique to comets rich in organic compounds. Lemon will make its closest approach to Earth on October 20 Gen 1st, 0.68 AU, or 101 million km, and swing by the Sun on November 8, 0.53 AU. After that, it will vanish into the outer solar system, not to return for over 1,150 years. Swan. A rare comet with a shallow orbit. Lemon isn't alone. Another visitor, CFD Launsenlinarshwu RR Swan, discovered in September 2020 Gen 5, will pass Earth on October 20th at a distance of 0.26 AU, 30 Gen 9 million km. Currently at magnitude +6, Swan is visible through binoculars and small telescopes, sporting a tail exceeding 5 degrees in length, roughly 10 times the diameter of the full Moon. What makes Swan unusual is its 4.5-degree orbital inclination relative to the ecliptic plane, an anomaly for a long Zan period comet from the Oort cloud, which typically arrive at steep angles. This has astronomers speculating about its origin or gravitational perturbations during its journey. Unpredictability. The comet's curse and allure. Comets are notoriously fickle. They can suddenly brighten due to outbursts or fragmentation, as seen with comet shoemaker Zan Levy Joe, which shattered into 20 Jan 1 pieces before colliding with Jupiter in 1990 Jan 4. Thermal stress. Solar radiation or tidal forces can cause nuclei to break apart, creating multiple comas and tails. For example, Sen Prishwasman, Zan Watchman Sen disintegrated into dozens of fragments in 2006, captured in vivid detail by the Hubble Space Telescope. Comets and the origins of life beyond their beauty. Comets hold clues to Earth's past. The late heavy bombardment 4 billion years ago delivered water and organic molecules to our planet via comet impacts. Comets like Lyushitsy Pre-Churyumov Jan Gerasimenko, visited by the Rosetta mission, and Wild R, studied by stardust, revealed amino acids and complex organic compounds, fueling the panspermia hypothesis. The idea that comets seeded Earth with life's raw materials. A cosmic double feature and meteor shower mark your calendars for October 20 Gen 1st. Lemon and Swan will grace the sky simultaneously, aligned with the Orionid meteor shower, peaking at 20 meteors per hour, and a new moon. Offering ideal dark Jan sky conditions, Lemon will shine in the northwest, Swan in the southwest, creating a rare celestial spectacle. The bottom line as October unfolds, these comets remind us of the cosmos's beauty and unpredictability. Whether Lemon and Swan behave as expected or surprise us with outbursts, they underscore our place in a dynamic universe and the enduring mystery of how life began. Stay tuned, the show has only just begun. Chapter 3. A Nursery for Moons. Watching Moon Formation. Unfold 620 Zan 5 light Zan years from Earth. Around a planet still in its cosmic infancy, something extraordinary is unfolding. The James Webb Space Telescope, JWST, has captured the first direct observations of a moon Zan-forming disk, a spinning ring of gas and dust circling an exoplanet called Comet. And within that disk, Webb detected chemical signatures that could spark moon birth: hydrogen cyanide, acetylene, benzene, propane, ethane, carbon dioxide, all carbon-rich molecules swirling in a structure that feels eerily familiar to scientists who study our own solar system's history. This is a game changer. For decades, we've theorized how moons form. We've looked at Jupiter's moons and guessed at their origins, but we've never watched the process happen. Until now. Think about Jupiter's 4 largest moons, the Galilean satellites discovered by Galileo in 1610. They orbit Jupiter in a flat plane, a clear clue they condense from a disk of material around the gas giant billions of years ago, much like how planets formed from the Sun's own disk. The two outermost Galileans, Ganymede and Callisto, are 50% water ice with rocky carbon Xan or Xen silicon cores beneath their frozen shells. For years, scientists suspected a circumplanetary disk, a moon-Xan-forming disk, once surrounded Jupiter, and that within it, moon raw materials clumped together. Now, with Country, we're seeing that exact scenario play out in another system. But real-time in astronomy is a tricky term. The light we're detecting from CETAR B's system left 620 Gen 5 years ago, back when Earth was in the Renaissance, and no one had even imagined planets beyond our solar system. Still, from our vantage point, we're witnessing moon formation as it unfolds, and the details are mind-blowing. The planet itself orbits a star that's only 2 million years old, still pulling in material from its own star's forming disk. This is a system in its absolute infancy, a planetary nursery where structure is forming on every scale, all at once. What stunned researchers most wasn't just the disk, it was the stark chemical split between the planet's moon-Xan forming disk and the star's planet-Xan forming disk. The planet's disk is packed with carbon-Xan-rich molecules, but no water. The star's disk, it has water, but none of that carbon chemistry. This segregation happened in just 2 million years, blink Xan of Jan and Xan fast in cosmic terms. It proves disk chemistry evolves rapidly and takes different paths based on local conditions, temperature, radiation levels, magnetic fields, all shape which molecules survive and which get torn apart. The implications go far beyond understanding moon formation. If we can map the chemistry of these disks in young systems, we can start predicting which exoplanets might host moons, and which of those moons could have conditions for life. In our own solar system, some of the best bets for life aren't planets, they're moons. Europa, Jupiter's moon, likely has a liquid water ocean under its icy crust, kept warm by Jupiter's gravitational tugs. Enceladus, Saturn's moon, shoots geysers of liquid water into space from an underground ocean, and those geysers hold organic molecules. If exomoons form with similar traits, the number of potentially habitable worlds in the galaxy skyrockets. We won't just look at planets in a star's habitable zone, we'll look at moons around gas giants, anywhere in a system. This expanding view of where life might exist isn't just theoretical. It's tied to the technologies we're building here on Earth, tech that could one day let us peer deeper into these distant moon nurseries, or even answer the biggest question of all, are we alone? Chapter 4. The Quantum Leap from Lab Curiosity to Practical Power. The United Nations named 2020 Gen 5 the International Year of Quantum Science and Technology. A fitting tribute because this year isn't just a celebration of 100 years of quantum mechanics. It's the year quantum computing finally shifted from a lab experiment to something that could actually change our world. In November 2020 Gen 4, Microsoft and Atom Computing dropped a bombshell. They'd successfully created an entangled 20 Gen 4 logical qubits. For anyone who follows quantum tech, this wasn't just a win, it was a giant leap toward building quantum computers that solve real useful problems. To get why this matters, let's break down the stark difference between the device you're using now and the quantum machines we're building. Classical vs. Quantum, the bit versus the qubit, your phone, laptop, even the world's most powerful supercomputers, they all run on bits. A bit is simple. It's either 0 or 1, on or off, true or false. Every video you stream, every simulation you run, every text you send. It's just billions of these binary digits being flipped at lightning speed. Quantum computers, they run on qubits, quantum bits, and they break all the rules. A qubit doesn't have to choose between 0 or 1. Thanks to a quantum quirk called superposition, it can exist as both 0 and 1 at the same time. Until you measure it, this isn't a metaphor. At the tiny scale of atoms and particles, matter acts like a wave, and waves can overlap, superpose with themselves. That's not just weird, it's powerful. Here's the math that blows classical computing out of the water. 2 classical bits can represent 4 values, lin, yi, shu, shi, but only one at a time, 2 qubits in superposition. They represent all 4 values simultaneously. 3 qubits, 8 values at once. This scales exponentially. A quantum computer with just a few hundred qubits could crunch calculations that would take a classical supercomputer longer than the age of the universe to finish. The catch: qubits are fragile. Until now, for decades, Quantum computing hit a wall. Qubits are incredibly fragile. They lose their quantum properties, a process called decoherence, at the slightest disturbance. A tiny temperature bump, a stray electromagnetic field, even a cosmic ray zipping through the lab. Any of these can scramble the qubit state and ruin the calculation. That's why quantum computers live in freezers colder than deep space. -450 degrees Fahrenheit, Fore, -270 degrees Celsius, and are shielded from the outside world. But even then, errors piled up so fast that most quantum calculations fell apart before they finished. The 2020 Gen 4 to 2020 Gen 5 breakthrough. Quantum error correction. This is the ability to spot and fix qubit errors without destroying the quantum state you're trying to compute with. Those 20 Gen 4 logical qubits Microsoft and Atom built. They're not raw hardware. They're qubits with built-in error correction, making them far more stable and reliable than anything we've had before. Entanglement. Einstein's spooky action as a superpower. There's another quantum trick that makes these computers special. Entanglement. Einstein called it spooky action at a distance, and for good reason. When qubits are entangled, measuring one instantly changes the state of the others, no matter how far apart they are, even light-years. This isn't just a party trick. Entanglement lets quantum computers solve specific problems, like searching massive databases or factoring huge numbers way faster than classical machines, and factoring big numbers. That's the backbone of modern encryption. Think your bank account, your phone's security. Quantum computers could crack that encryption, or help us build unbreakable quantum encryption instead. The global race for quantum supremacy. This isn't just a science story, it's a geopolitical one. Governments and companies are pouring billions into quantum tech because it's not just cool, it's a strategic game changer. Early 2020 Gen 5, Japan announced a $7.4 billion investment in quantum research. Spain followed with $900 million. Total global public funding for quantum tech now tops $10 billion. The private sector is even more fired up. Google claims its quantum processors already solve some problems exponentially faster than classical supercomputers. IBM has a roadmap to build a 2 Gen 100 Zen logical Zen qubit system by 2020 Gen 8. Startups are experimenting with wild alternatives using photons, light particles instead of superconducting circuits or trapping ions, charged atoms instead of solid Zen state chips. Each path has pros and cons, but the race is on. The philosophical kick. Harnessing the universe's native language beyond the engineering, quantum computing hits a deeper chord. These machines don't just compute, they operate on the same rules that govern the universe itself. The quantum mechanics that makes qubits work, it's the same science that shapes atoms, builds molecules, and makes stars shine. In a way, quantum computers let us speak the universe's native language to solve problems we could never touch before. Like, for example, mastering nuclear fusion, a breakthrough that's unfolding right alongside quantum tech and could redefine how we power our world. Chapter 5. Capturing the Stars. How we're inching closer to fusion power. On February 12, 2020 Gen 5, scientists at France's West Tokamak reactor pulled off something historic. They held blisteringly hot plasma steady for 20 Gen 2 minutes and 17 seconds, smashing the previous record by over 4 minutes. That plasma hit 50 million degrees Celsius, 3 times hotter than the sun's core. If you're new to fusion research, that might sound like a small win. After all, the sun has kept fusion running for 4.5 billion years without any human help. But here's the thing, creating and controlling a star-den-like reaction on Earth is one of the hardest challenges in science and engineering. This 20 Gen 2 Gen minute milestone, it's a giant step toward turning fusion into the clean, limitless energy source we've dreamed of for decades. What is fusion, and why is it so hard? Fusion is how stars make energy. They squeeze atomic nuclei so tightly that they overcome their natural repulsion and merge, releasing a burst of power. In the sun, this works because its massive gravity crushes the core, 15 million degrees Celsius, into a fusion furnace. On Earth, we don't have that gravity, so we need 2 things to make fusion work: extreme heat, way hotter than the sun's core, hence 50 million degrees Celsius to force nuclei together. A way to hold the plasma, that super-Zen hot gas plasma, can't touch any physical surface. Nothing on Earth can withstand 50 million degrees Celsius without vaporizing instantly. The solution? Magnetic confinement. Tokamak's donut-zen-shaped reactors use powerful magnetic fields to create an invisible cage that suspends the plasma in a vacuum, keeping it far from the walls. Like holding a ball of fire with magnets, except the fire is hotter than the sun. Why 20 Gen 2 minutes matters? Hint, it's about power plants. The West Tokamak's 20 Gen 2 Gen minute run isn't just a numbers game. Future fusion power plants need to operate continuously. You can't generate electricity economically if your reactor shuts down every few minutes. This record proves we're solving the engineering headaches of steady Gen state operation, managing heat flow, keeping the plasma stable, and stopping instabilities that break the magnetic cage. Even more exciting, the previous record 17 minutes was set just weeks earlier, in January 2020 Gen 5, by China's East Tokamak, 2 major milestones in a matter of weeks. That's momentum proof. We're not just inching forward, but accelerating. The private sector is racing to. Governments aren't the only ones chasing fusion. The private sector is blowing up with innovation, and 2020 Gen 5 has been a breakout year. ETI Technologies. In April 2020 Gen 5, they simplified how they create and stabilize plasma using a field Gen reversed configuration, FRC, a more compact design than traditional tokamaks. Previously, FreeVS needed complex hardware to generate plasma and smash it into the center. ITER figured out how to do it all in one spot with just neutral beam injection, cutting costs and boosting efficiency. They're now on track to demonstrate net energy gain, more energy out than in by the end of the decade. Commonwealth Fusion Systems, they're building a pilot plant called Spark outside Boston, set to turn on in 2020 Gen 7. Helion Energy, they've finished initial tests on a new machine that uses a different magnetic setup to hit break Gen even. Energy in though new energy out, general fusion. Canada, they're taking a totally different approach, compressing plasma with mechanical force instead of just magnets. This diversity matters. Fusion is so hard that there's no single right way to do it. Having multiple teams testing different ideas means we're more likely to crack the code faster. From it works to it powers our homes, we already know fusion is possible. In December 2020 Gen 2, California's National Ignition Facility, NIF, achieved fusion ignition for the first time. The reaction put out more energy than the lasers used to start it. That was a scientific win, but turning that lab experiment into a power plant means solving dozens of engineering puzzles. Fuel supply, fusion runs on deuterium extracted from seawater. 1 atom in every 6,500 hydrogen atoms. The oceans have enough to power us for millions of years, and tritium, bred from lithium, which is abundant radiation resistance. Fusion neutrons make reactor walls radioactive, so we need materials that can handle years of bombardment without breaking down. Heat capture, we need to turn that 50 million degrees Celsius plasma heat into electricity efficiently. Cost, it all has to be cheap enough to compete with solar, wind, or fission. The big question: when? Skeptics love to say fusion is 20 years away, and always will be a joke that's stuck around for 60 years. But 2020 Gen 5 feels different. We've got technological breakthroughs, billions in investment, public and private, and an urgent need for clean energy to fight climate change. Optimists think we could see the first commercial fusion electricity on the grid by the early 2030s. Will it be easy? No. Will there be setbacks? Almost definitely. But for the first time, it's plausible that a kid born today might grow up in a world where fusion power is as common as solar panels. And maybe that kid's generation will use fusion gen-powered spacecraft to explore the solar system, following comets, visiting asteroids, and digging deeper into Mars' secrets. Speaking of Mars, it's still dropping hints that it once hosted life. Chapter 6. Leopard spots on Mars, the strongest hint of ancient life yet. In July 2020 Gen 4, NASA's Perseverance rover drilled a tiny core sample from a rock nicknamed Charfalls in Mars's Jezero crater. At first glance, it was just another chunk of red dirt. But to mission scientists, it was the most puzzling, complex, and potentially important rock they'd ever found on the red planet. A year later, after rigorous peer review, the findings landed in Nature, September 2020 Gen 5, and they're the strongest evidence yet that Mars might once have hosted microbial life. Key word, might, because in astrobiology, nothing is ever as straightforward as it seems. The right rock in the right place, Charfalls sits in an ancient riverbed within Bright Angel, a region Perseverance has been exploring for years. Billions of years ago, water rushed through this area, carving channels as it poured into Jezero crater, which back then was a deep lake. The rock itself is sedimentary, made of clay and silt and on Earth. This is exactly the kind of material that preserves fossils and chemical traces of ancient life. Perseverance's instruments found exactly what astrobiologists hope to see: organic carbon, the building blocks of life, sulfur, oxidized iron, and phosphorus, nutrients life needs. But what stopped scientists in their tracks? Leopard spots, tiny specks packed with iron phosphate and iron sulfide, scattered through the rock like a big cat's fur. On Earth, when microbes eat organic matter, they often leave these two minerals behind as metabolic waste. The pattern in chaffles, it looks just like what we see in terrestrial rocks that hold fossilized microbial communities. The catch: chemistry can be tricky. Here's the problem: you don't need life to make these spots. Natural processes, hydrothermal vents, volcanic activity, even asteroid impacts, can also create iron-rich mineral deposits that look identical to biological ones. Distinguishing between made by life and made by geology is the hardest part of astrobiology, especially when you're doing it from millions of kilometers away with a rover's instruments. That's why scientists call this a potential biosignature, not proof of life. A biosignature is something that could come from life, but needs more evidence to confirm it. It's a deliberate, cautious approach, and for good reason. The scientific community learned this lesson the hard way in 1996 when researchers claimed a Martian meteorite found in Antarctica had bacterial fossils. Years of followed-up research couldn't definitively prove or disprove it, reminding everyone that extraordinary claims need extraordinary evidence. Why this rock is different? It's younger, what makes the Chaffles finding even more exciting. The age of the rock. The Bright Angel Formation is younger than most of the ancient rocks Perseverance has studied until now. Scientists assumed signs of life, if they existed, would only be in Mars' oldest rocks, from when the planet had a thick atmosphere and liquid water on its surface. Finding potential biosignatures in younger rocks flips that idea on its head. Maybe Mars stayed habitable longer than we thought. Or maybe habitable conditions returned later, like when volcanic activity melted subsurface ice, creating temporary oases where microbes could survive. The next step: bring the sample home. This core sample, officially named Sapphire Canyon, after a Grand Canyon waterfall, is one of 30 Perseverance has collected, stored in sealed titanium tubes. Each tube is a snapshot of Mars geology, rocks from different eras, different environments, all chosen for their potential to hold clues about the planet's past. The ultimate goal: the Mars Sample Return Mission, a joint NASA-ESA effort to bring these tubes back to Earth. It's a massive technical challenge. We've never fetched rocks from Mars before, but it's critical. On Earth, we have instruments far more powerful than anything we can send to Mars, tools that can measure isotope ratios, hunt for amino acids, and examine mineral structures at the atomic scale. Until then, Sapphire Canyon sits in Perseverance's belly, a tiny piece of Mars that could be the biggest discovery in astrobiology history, or just really interesting geology. The thrill of uncertainty, this ambiguity, is frustrating. But it's also why we're hooked. We're living in the first era where we might actually answer the question: is there life beyond Earth? Not with guesses, but with direct observations. That answer might come from Mars, it might come from Europa, Jupiter's icy moon with an ocean, or Enceladus, Saturn's moon that shoots water geysers. It might come from analyzing the atmospheres of exoplanets. But one thing's clear: the search is moving faster than ever, driven by tech that didn't exist a generation ago. And some of that tech, especially artificial intelligence, is advancing so quickly that it's reshaping how we explore not just Mars, but the entire cosmos. Chapter 7: The Silicon Mind Eyes Hype versus Reality. And what's next? In 2020 Gen 4, the average company dropped $1.9 million on generative AI. But here's the kicker: less than 30% of AI leaders said their CEOs were happy with the return. That gap tells you everything about where we are in the AI revolution. The tech works, sometimes spectacularly, but turning cool AI tricks into real business value, way harder than the hype led us to believe. 2020 Gen 5 is the year that reality check hit. Companies are ditching "let's test AI for fun" and focusing on what problems can AI solve better than anything else. It's a recalibration, and it's pushing AI from labs into the real world faster than ever. AI that's actually accelerating science. The tech itself isn't slowing down. In September 2020 Gen 5, Microsoft unveiled IBM DNA system. That's a game changer for protein research. Proteins are life's molecular machines. Their 3D shape determines what they do, think, fighting diseases, building cells. Simulating how they fold and interact used to take supercomputers weeks, because proteins have thousands of atoms, and their behavior depends on tiny quantum level interactions. IBM D cuts that time down to hours. For drug discovery, this means faster development of new therapies for cancer, Alzheimer's, or rare diseases. For enzyme engineering, it could lead to greener biofuels or better ways to clean up pollution. This isn't AI for show, it's AI solving problems we've been stuck on for decades. Mapping the brain faster than humans ever could. AI is also rewriting how we study the human body, starting with the brain. Researchers at UCSF and the Allen Institute built Cell Transformer, an AI model that created the most detailed map of a mouse brain, ever 1,300 regions and subregions, including areas no human had ever identified. How? It analyzed spatial transcriptomics data, basically, mapping which genes are active in which cells and where those cells sit in the brain. AI spotted patterns, humans missed boundaries between regions, hidden substructures that would have taken decades to find manually. And this isn't just for mice. The same tech can map cancer tumors, revealing how they grow and spread. It's opening new doors for personalized medicine, all because AI can process data faster than any team of scientists. Then there's the breakthrough from University College London, ULI, that identifies brain cell types from their electrical signals, with 95% accuracy. For decades, neuroscientists could record neuron activity, but they had no idea what kind of neuron they were watching without using messy genetic tests. This AI reads the tiny electrical spikes different neurons make, like learning a language only neurons speak. It could revolutionize brain-computer interfaces, BCIs, or treatments for epilepsy. Researchers warn it's still years from clinics, but it's a huge step. AI moves from pilots to everyday tools by 2020 Gen 5. Gartner predicts 75% of companies will stop testing AI and start using it full Gen time. We're talking AI agents, not the scripted chatbots of 5 years ago, but software that can analyze 1/100's Jan-page legal contracts and flag risks. Manage supply chains, predicting shortages before they happen. Write and debug code, saving developers hours. Even give personalized medical advice, though always paired with doctors for now. These agents raise big questions. If an AI makes a mistake that hurts someone, who's responsible? The developer, the company using it, the user. In late 2020 Gen 5. A Colorado lawsuit made this real. Parents claimed an AI chatbot contributed to their teen's suicide by having manipulative conversations. This case could set rules for AI liability rules. We desperately need as AI creeps into sensitive areas like mental health or education. The big flaw in today's AI and how we'll fix it for all its wins. Today's AI has a big problem. It doesn't understand anything. Large language models, LMs like ChatGPT, learn patterns from internet text, so they can write coherent sentences, but they lack common sense. They make up facts called hallucinations. Get tricked by weird inputs and can't verify if their answers are right. The next generation of AI will fix this, though no one's sure exactly how yet. Some researchers are building composite AI, systems that combine multiple specialized models, one for math, one for writing, one for logic. Instead of relying on one big model, others want to pair AI with robots, giving it a body so it can learn about the physical world like humans do, touching, seeing, moving. Then there's neuromorphic computing, chips that mimic the brain's structure, making AI more efficient and better at reasoning. We're still early, and that's exciting. Here's the truth, we're just starting to figure out what AI can do. The excitement is real. I can speed up science, make work easier, and solve big problems. But so are the risks, bias, privacy, liability, and knowing where to draw the line. As we build more powerful AI, we need to build more wisdom to use it responsibly. That same wisdom applies to another big mystery, one that's even bigger than AI. The stuff that makes up most of the universe but we can't see. Chapter 8, The Illusion of Darkness. What if dark matter and dark energy don't exist? For nearly 100 years, cosmologists have agreed on one unshakable truth. Most of the universe is invisible. Ordinary matter, stars, planets, even us, adds up to just 5% of the cosmos. Another 20-7% is dark matter, invisible, but we know it's there because its gravity tugs on galaxies, keeping them from flying apart. The remaining 60-8%. Dark energy, a mysterious force stretching the universe apart faster every day. Together, they shape everything we see. But what if they're not real at all? The paper that could upend cosmology in October 2020 Gen 5, Rajendra Gupta, an adjunct physics professor at the University of Ottawa, dropped a paper that sent shockwaves through the field. His radical idea: forget exotic invisible substances. What if the universe's fundamental forces like gravity are weakening over time? Here's the game-changing logic. We've always assumed gravity's strength is constant. It was the same a billion years ago. It's the same today. And it'll be the same a billion years from now. But Gupta says that assumption might be wrong. What if gravity was slightly stronger in the past and will be slightly weaker tomorrow? That tiny gradual change could explain everything we currently blame on dark matter and dark energy. Distant galaxies rotating faster than expected. Not dark matter, just stronger gravity pulling on them back then. The universe expanding faster over time. Not dark energy, just weaker gravity failing to slow the expansion now. In Gupta's model, there's no need for weird particles or unknown energies. We just need a universe where the rules of physics evolve as space itself ages. It's not the first challenge, but it's the most promising. This isn't the first time someone has tried to rewrite the rules to skip dark matter. Modified Newtonian dynamics. MOND has been around for decades. It explains how galaxies spin without invoking dark matter halos. But MOND fails when you zoom out. It can't explain how galaxy clusters hold together or the pattern of hot and cold spots in the cosmic microwave background, the faint afterglow of the Big Bang. Gupta's model, dubbed CCJTL, fixes that. It uses a single parameter that changes with both time and local matter density. So it works for small scales, galaxies, and big scales, the entire universe, without adding any new ingredients. For the first time, an alternative theory might explain all the phenomena dark matter and dark energy do, with fewer moving parts. The data is already shaking the standard model. Gupta's timing couldn't be better. Other recent data is already making the dark universe model wobbly. In April 2020 Gen 5, the Dark Energy Spectroscopic Instrument Design, the most powerful tool for studying dark energy, released results showing dark energy might not be constant. It could be weakening over time, a detail the standard model can't account for. If dark energy is changing, we need to rewrite our theories, and that raises a bigger question. Does dark energy even exist, or is it just a placeholder for a rule we haven't figured out yet? Meanwhile, experiments searching for dark matter particles keep coming up empty. The Lux-Gen Zeppelin detector, or most sensitive tool for hunting dark matter, has run for years and found nothing. It's ruled out huge swaths of what we thought dark matter could be. No WIMPs, weakly interacting massive particles. No axions. Nothing. Each null result makes dark matter's possible forms weirder and less likely. Some physicists are starting to wonder, are we chasing a ghost? Why ditching dark matter and dark energy is so hard for all the cracks in the standard model. Abandoning dark matter and dark energy isn't easy. They explain too much. Why galaxies don't fly apart as they spin. Why galaxy clusters stay intact instead of dispersing. Why gravity bends light, gravitational lensing, in exactly the places we see it. Why the cosmic microwave background has the exact pattern of hot-cold spots we observe. Any new theory, including Gupta's, has to explain all of these phenomena, at least as well as the dark universe model. Gupta's work is a step in the right direction, but it needs to survive rigorous testing against every piece of cosmological data we have before it can replace the standard model. The big question: how do we know what's real? This debate isn't just about physics. It's about a fundamental scientific question. How do we distinguish real things from the assumptions we use to explain them? Dark matter and dark energy have never been directly detected. We infer their existence from how gravity acts, how matter moves, how space bends, but inference can trick us. For centuries, astronomers thought planets orbited the sun in perfect circles because perfect shapes felt right. The truth turned out to be ellipses, simpler. Once we let go of our bias for perfection, could we be making the same mistake now, assuming the universe is filled with exotic, invisible stuff? when the real answer is just that our equations need a small tweak. The next few years will settle it, we won't have to wonder for long. New telescopes will soon give us the data to test Gupta's model, and the dark universe with unprecedented precision. The Vera C. Rubin Observatory, launching late 2020 Gen 5, early 2020 Gen 6, has the largest digital camera ever built. It'll image billions of galaxies, mapping how matter is distributed across the cosmos and testing if dark matter's gravity fingerprint is real. The Nancy Grace Roman Space Telescope, launching 2020 Gen 7, will measure the universe's expansion rate with pinpoint accuracy, revealing if dark energy is changing, or if it exists at all. In the next few years, we'll either confirm that dark matter and dark energy are real, or we'll have to completely rethink how the universe works. The beauty of science, it's never finished either way. This is what makes science extraordinary. It doesn't cling to certainty. Every answer opens new questions. Every proven theory gets challenged. Sometimes the biggest discoveries don't come from finding something new. They come from realizing what we thought we knew was just the beginning. The universe's darkest mystery might not be dark matter or dark energy. It might be that we've been overcomplicating things all along. Chapter 9. The Space Between. How we're turning space into a place we can visit. While scientists debate dark matter and engineers build quantum computers, another quieter revolution is unfolding. We're making space accessible. On October 8, 2020 Gen 5, Blue Origin launched its 15th space tourism mission. The passengers floated weightless for minutes, stared at Earth's curved edge against the black, then landed safely. For them, it was life-changing. The overview effect astronauts talk about, where seeing our planet from space shifts how you think about humanity. For the space industry, it was just another day at the office. That's the big shift here. Spaceflight isn't just for governments and trained astronauts anymore. A generation ago, you needed years of training and a spot on a NASA shuttle to reach orbit. Now, private companies fly paying customers. The price tag's still out of reach for most, but as tech improves and competition heats up, costs are dropping. This isn't just space tourism. It's the start of building a world where humanity lives beyond Earth. From rockets to a solar system infrastructure, SpaceX changed the game with reusable rockets. Before, rockets were one zan and zan done, crashing into the ocean after one flight. Now, SpaceX lands boosters back on Earth, or drone ships to refly them, slashing launch costs by 70% or more. Blue Origin is building its own reusable New Shepard and New Glenn rockets. Other companies, they're working on spaceplanes, like Virgin Galactic's Unity, orbital hotels, Orion Span's Aurora Station, lunar landers, Intuitive Machines, Nova GNC, and even Mars mission blueprints. This isn't random, it's infrastructure. SpaceX's Starship, the biggest, most powerful rocket ever built, isn't just for show. It's designed to carry cargo and eventually people to the moon. And Mars, NASA's Artemis program, wants to put astronauts back on the moon by 2020 Gen 5. Then build a gateway space station in lunar orbit, testing tech for longer trips to Mars. China is building its own space station, Tiangong, and planning a lunar base. India, Japan, and Europe are all developing their own spacefaring tools. We're not just visiting space anymore, we're building the roads and houses to stay there. The hard part. Living in a hostile place space doesn't want us to survive. No air, no water. Temperatures swinging from minus 250 degrees Fahrenheit to 250 degrees Fahrenheit. Solar radiation that can damage DNA. Cosmic rays that pierce metal. To live there, we need to solve problems we've never faced on Earth. Life support. Recycling every drop of water, every breath of air. No resupplies from Earth for Mars missions. Resource extraction. Mining the moon for water. Frozen in craters or asteroids for metals. Launching everything from Earth is too expensive. Energy, solar panels work in space until a dust storm hits Mars. Small nuclear reactors might be the backup. Psychology. Imagine living in a metal box with 3 people for 6 months, 150 million miles from home. Isolation and stress will be as big a threat as radiation. Why bother? The why matters, critics ask. Why spend billions on space when we have problems on Earth? The answer's split into 2 camps, pragmatic and aspirational. Pragmatic: space is a backup plan. Earth is fragile. Asteroid impacts, supervolcanoes, climate collapse, even nuclear war could end civilization. Spreading to Mars or the moon means humanity survives, no matter what. It's also a resource goldmine. Asteroids have more nickel, iron, and platinum than we've ever mined on Earth. Aspirational, it's human nature to explore. Our ancestors left Africa to populate every continent. Explorers crossed oceans to find new lands. Scientists peer into black holes to understand the universe. Space is the ultimate frontier, not because it's empty, but because it's full of questions we haven't asked yet. Space doesn't exist in a bubble, it's connected to everything. Here's the key: space exploration isn't separate from the tech we've been talking about. It's all linked: quantum computers. They could optimize Mars mission trajectories or create unhackable communication between Earth and a Mars base. Fusion reactors, a fusion-powered rocket, could cut travel time to Mars from 6 months to 2 weeks, making long trips feasible. AI, it'll run life support systems, navigate rovers autonomously, and analyze data from Mars rocks, like Perseverance's leopard's ant spot sample, faster than humans. Astrobiology, finding life on Mars or Europa, tells us where else to look in the galaxy, and how to build habitats that mimic those conditions. Everything connects. A comet's chemistry explains how planets form. A quantum computer's qubits reveal how the universe works at its smallest scale. A fusion reactor copies the sun's power. An AI mapping the brain shows how complexity grows from simple rules. And a Blue Origin flight. It turns space from a concept into a place. One, where more of us might live someday. 2020 Gen 5. A chapter in the big story: the breakthroughs of 2020 Gen 5 quantum computing. Fusion, Mars life hints. AI, space tourism aren't separate stories. They're chapters in one big narrative. Human beings don't just exist. We are curious, we build, we explore. We're not just advancing one field at a time, we're cross-gen pollinating ideas. A tech for quantum computers might help build better fusion reactors. A lesson from Mars life searchers might teach us about AI's limits. And every time a private company launches a tourist into space, we take one more step toward a future where do you live could mean Earth or Mars or a lunar base. The space between Earth and the stars isn't empty. It's where we're building our next home. Chapter 10, The Horizon. We're just getting started. We began with an asteroid that slipped past Earth unseen, and a comet brightening our October skies. 2 small reminders that the universe is alive, dynamic, and that our place in it is both tiny and extraordinary. From there, we wandered to a distant planet where moons are being born from a dusty disk, echoing how our own moon formed billions of years ago. To quantum computers edging towards solving problems no classical machine ever could. To fusion reactors holding suns and hot plasma long enough to hint at a future free of fossil fuels. We leaned in to study a Mars rock with leopard spots, a potential sign of ancient microbial life, still unconfirmed, waiting for the day we can bring it home to Earth. We watched AI map brains, simulate life-saving proteins, and raised tough questions about who's responsible when machines make mistakes. We dared to ask, what if dark matter and dark energy, those invisible giants we've blamed for shaping the cosmos, don't exist at all? What if we just need to tweak our equations, not invent new substances? And we noted how space travel is quietly shifting from government secret to business as usual. Still expensive, but getting closer to being something more of us might experience. Uncertainty isn't failure. It's where discovery lives. Every one of these steps comes with doubt. Quantum computers might hit a wall we can't climb. Fusion might stay 20 years away for another 20 years. That Mars rock's biosignature could turn out to be just weird geology. AI might plateau, or dark matter might prove stubbornly real. Space might stay the domain of billionaires, not everyday people. But uncertainty isn't futility. It's the soil where science grows. Science isn't a list of facts, it's a process. Ask a question, test it, revise when it's wrong. The questions we're asking now are the biggest we've ever posed. What is the universe really made of? How did life start, and is it rare? Can we harness the power of stars to power our world? What is consciousness, and can a machine have it? Are we alone in the cosmos? How do we make sure our technologies help, not hurt? These questions don't have easy answers. If they did, they wouldn't matter. The value is in the search, the things we learn along the way, the tools we build to dig deeper. The way our perspective shifts when we realize we were wrong. Look how far we've come, and how far we could go a century ago. We didn't know the universe was expanding. 50 years ago, we hadn't sent a rover to Mars or found a single planet around another star. 25 years ago, quantum computers were lab toys, and AI could barely read handwritten numbers. The pace of change is accelerating, driven by better computers, smarter materials, and a hunger to know more. What might the next decade bring? If fusion goes commercial, energy abundance could lift billions out of poverty, power cities without carbon, and make impossible projects like Mars bases feasible. If quantum matures, it could speed up drug discovery, finding cures for cancer faster, revolutionize cryptography, making data unhackable or breaking old security, and reshape how we make everything from batteries to plastics. If we find life beyond Earth, confirming biosignatures on Mars or in an exoplanet's atmosphere would be humanity's biggest win-proof. We're not alone, that life is a cosmic rule, not a fluke. If AI advances wisely, it could become a scientific partner, generating hypotheses, designing experiments, analyzing data too big for humans, freeing us to focus on the why, not just the how. If space opens up, the moon's water, asteroid metals, and Mars resources could become part of our shared future, no longer just space stuff, but tools to build a better world. With great power comes great responsibility. These possibilities aren't without risk. Quantum computers could break the encryption that protects our banks and militaries. Fusion could be weaponized. AI could amplify bias, take jobs, or be used to control people. Space exploration could contaminate other worlds or bring alien microbes home or widen inequality. Navigating this isn't just about tech skill, it's about wisdom. We need to ask not just what can we do, but what should we do? We need diverse voices in the room, not just scientists or billionaires, transparency about risks, and humility about how little we know. Technology isn't good or bad, it's a mirror. It shows us what we value, and it amplifies our choices. We're all part of this story. It's October 2020 Gen 5. We're watching comets glow, reading about quantum entanglement, cheering fusion records, and waiting for Mars answers. The universe keeps turning. Stars are born, galaxies collide, moons form, comets plunge toward the sun, and here on Earth, one small blue dot, we've learnt to look up, ask why, and build tools to find out. Thank you for joining me on this journey through the latest discoveries. If you loved this exploration, hit like and subscribe. Science doesn't stop, and neither will we. Every answer opens a new mystery, every question leads to something bigger. A quick note, all the info here is based on current research that's still evolving. Keep looking up, keep asking questions. Remember, you're not just watching this story unfold, you're part of it. Wherever you are, whatever time it is, good night and keep wondering.